Hey guys, thought I'd keep this blurry to keep you in suspense. Just can't get it to focus. So today is our last topic that we are doing today through Wednesday, and it's Introduction to Limits. And I kind of already had all these notes written out, so I'm going to jump back and forth. And it's a lot of table making, so to cut down on the length of the video, I'm just going to take my notes as is and just like show you the table instead of having you watch me compute every single number, and we'll talk about it. So for those of you who will be taking EP Calc next year, this is a worksheet you might actually use. We use it in Precalc to introduce limits to you. So we talked about limits back in our second unit with rational functions. Do you remember how you had to use the limit notation on your quiz? Maybe, maybe not. But we're revisiting this again. And so these first examples are going to show you how you find limits with tables. And so remember, you can find the limit of a specific value. So if we had the limit of a function as x, say, approaches 3, well, we have to figure out what that function is doing to the right and the left of the specified x value. So let's jump into this. So consider the function x to the fourth minus 1 all divided by x minus 1. So the table approach, again, this is already a pre-made table, just kind of exploring what's going on, 1.8, 1.9, etc. You can read those. And if you put each of those values into the calculator and put them into this function, you'd get these values here. You got 11.8, 13.3, and then you see, oh, it's kind of leveling off. I've got 14.8, 14.9, 14.998. So what do you think happens to the values of the function as x approaches 2? We know we're approaching 2 because these values are getting closer to 2. And it's from the left, right here, because these values are coming in from the left of 2. So what would be your guess? It's approaching 15. Because as you did 1.99, 1.999, etc., it's getting closer and closer to 15. So the same table was made. If we were in class, we would have done this as kind of our notes, as our lesson, but here we are, of 2 from the right. So here's the same equation, but now we're taking 2 from the right. So we're coming into 2 from the right, and as we see, as x gets closer to 2, f of x is getting closer to 15. And so what happens to the values as x approaches 2 from the right? It approaches 15. So therefore, we can state the limit of f of x as x approaches 2 equals 15, because from both sides, from the left and the right, f of x was getting closer to 15. Okay? And you can read this little note here for yourself. The same answer might be found by simply substituting 2 into x in the function. And if we graph this, I'll spare you the graphing calculator because there's kind of a lot for me to talk about here. If we went from 1.8 to 2.2 on your calculator, again, using our function up here. Okay, Aiden, you got to relax a little bit, please. This is what the graph would look like. And it appears that, again, from both sides, there's no asymptotes or anything. It's coming right into 15. We don't have 15 here, but it's a continuous from left to right. Again, if you just put 2 into the function, you would get 15. You're like, well, what's the point of the table? Well, sometimes tables can be useful and sometimes it can't be, but so we're going to show you all different ways to go about these, so bear with me here. I'll try to move along. So again, looking at the same function, this time we're looking at 1, as you can see from the left and from the right. Coming in from the left, f of x gets close to 4. Coming in from the right, it also gets close to 4. This time, though, when you substitute 1 into the function, you get 0 over 0. Obviously, you have 0 in the denominator there, which is undefined. So what does this function look like graphically as you approached 1 from either the right or left? So if we put this graph into our graphing calculator, you'd find that there's a hole at 1. All right, so that's why sometimes just substituting in it doesn't work. The table shows us that in this case, my limit's going to be 4 from looking at the table. All right, here are some other ones, just different situations, pulling sine into it here. Again, we want to know what's the limit of this function as x approaches 0. So you take values from the left of 0 that are pretty small, and then also values coming in from the right. And I like to draw a line here just to show. So as I'm coming in from the left, f of x is getting closer to 10. And as I'm coming in from the right, it's also getting closer to 10. So the limit here would be 10. Another situation, another function. Whoop, come on and focus. Again, x is approaching 0. You pick the values coming in from the left. We're getting closer to 2.718. Same deal here, 2.718. You might not ring a bell that, oh yeah, this is E, but it is E. If this was a quiz or something and you said 2.718, you'd get credit for that. But this, interesting enough, is the limit here is E. That's just super exciting for us. All right, another example, because between today, tomorrow, and Wednesday, you'll see questions like this, and it's just one worksheet a day. Not trying to overwhelm you here, just trying to expose you to topics that you will see next year in calculus. Even if you take honors calc, you'll be seeing this too. Anyways, I'll stop rambling. What else is new? My last video. Oh gosh. All right, so the limit as x approaches 1 of f of x, where f of x this time, you have a piecewise function, and the answer is already there because this is my key. But at any rate, so where we want to approach, this thing could just stay focused. That would be just awesome. What was it? 1? It's 1 because I can read off of my phone. So again, this would be you picking values coming in close to 1 from the left and close to 1 from the right. And in both cases, you see that f of x is approaching 4 in that case. Now, in this case, if we look down here to see x is greater than 1, we'd have 14 minus 10 over 1, which would be 4. And when x is smaller than 1, if I checked out just substituting 1 in there, we'd have 1 minus 1, 1 minus 1. This one would be, we'd have 0 in the denominator, so that wouldn't be a help for that one. Part D, if we had the limit of x divided by x minus 2, the limit as x approaches 2, again, you'd make your table, choose values from the left and values from the right of 2. And in both cases, they're not this, well, not in both cases, but in these two situations, you do not get the same f of x value. And so that's because one's going down to negative infinity, one's going up to positive infinity. So this is a case where you write DNE, which stands for does not exist. That's the lingo notation that you used when there is no limit. Okay. Here's another situation. As x approaches 0, sine of 1 over x. So again, you're coming into 0 from the left, 0 from the right. This one, you get a negative 0.827 and a 0.827. If you actually graph this one, you'd see that it oscillates, and it's not actually coming in at the same y value from both directions of 0. So again, this is another example of does not exist. For f, the absolute value of x divided by x of 0, once again, you get a negative 1 and a 1. This is a does not exist example because it's coming in from two different numbers, so it's not the same value. Okay, another one here. Now let's change it up. As x approaches infinity, so as x gets bigger and bigger and bigger, putting these large values in for x, you're going to see that f of x approaches 1.5 or 3/2. You should see that anyway based off of what we talked about back in Unit 2 with our rational functions. Thinking about your horizontal asymptotes and things. Come on, I think I skipped G, okay. So again, the limit as x approaches infinity, if you, again, trying to save on time here, put these values in for x, you're going to see that this one oscillates as well, and so it's another example of does not exist. So this is a good chance to switch to my page of behavior associated with a non-existent limit. All right, so with your DNEs, there's 3 basic situations. You'd have a limit that's DNE if f of x approaches a different number from the right and the left of that c that you're looking for. So here's a visual example of that. Here it's from the right, it's coming into here. From the left, it's over here. A second instance is f of x increases or decreases without bound as x approaches that c value, which is basically your vertical asymptote that you're talking about. And then lastly, the oscillation, we saw that in the last couple of examples between two fixed values as x approaches c. That's another example of DNE. So I actually feel like I covered a lot in what we just talked about. I'd like to give you the formal definition here really quick. So, if f of x becomes close to a single number L as x approaches c from either side, the limit of f of x as x approaches c is L. So capital L, but in this case is that limit value. So again, limit of f of x as x approaches c equals your L. And some of these I already did, as I realized. So approaches that we've talked about so far, you have the numerical value, which is approach, which is your table, graphical by hand or calculator, and then analytic is your using your algebra or your calculator. I'm just trying not to overdo everything that I have here. Some basic properties, which I'll take a picture and post later, but there are 10 basic properties here that you can use with your limits. I'm not going to read every one to you because I don't think that's something that you need me to, but we'll show you how you apply them. So let's jump into some where you would actually do it out. So find the limit as x approaches 2 of 4x squared plus 3. So if you look below here, this is a case where you can use your properties. We could also just say that, okay, well, I'm really going to actually find, I can substitute in 2 and see what happens. So the limit as x approaches 2, so that's going to be 4 times 4, I don't know why I just put a parenthesis there, I shouldn't have done that, plus 3. So that's 16 plus 3, that's 19. So that's my answer. That's a case where it worked out fine. You didn't have to do a table in this case because you're able to figure out the limit in this situation from just substituting in. For this one, x squared plus x plus 2, all divided by x plus 1. If we put 1 in here, that's fine. Because your denominator does not equal 0 when x equals 1. So again, putting 1 into your function here, we're going to get our limit is 2. Simple enough. Same thing for 3. It's okay to put 0 in here. So I'm going to get the square root of 4, which is 2. So my limit as x approaches 0 of root x squared minus 4, I should say, equals 2. Number 4, same deal. If it would focus, come on. The limit as x approaches 3 of the cube root of 2x squared minus 10. Again, another situation where you can just put 3 in here. You will get 2 as your limit. All right, so this is a situation here. The limit of x cubed minus 1 over x minus 1 as x approaches 1. So this case, if we took the approach of just substituting in, we're going to see that when we do that, right, we would get a 0 in the denominator. And this is similar to the first one on that computer-generated packet that I had over there. But anyways, so, right, if I put 1 in here, that's a problem because I'll get a denominator of 0. So in this case, if we look down here, we can factor x cubed minus 1. That's the difference of perfect cubes. The numerator will factor into this here. Those guys will cancel out. So we're really looking at the limit as x approaches 1 of x squared plus x plus 1. So if I put 1 in here for x, my answer is 3. Okay. I don't know if I need to, we'll skip that for now. Here's another example. If I put negative 3 in right away for x, you will get 0 over 0 by direct substitution. This is called the indeterminate form because from the form alone, like we talked about, we can't determine the limit. So just like above, like I said, we need to factor or rationalize the numerator. So here we go. This is what we need to do. We factor the numerator. The x plus 3's cancel out. Okay. I'm going to put negative 3 in for x, so my limit for this case is negative 5. Looking here on the back, this is my last algebraic example, then I just have some graphs I want to look at really quick with you. Here's another example. If you put 0 in, you're going to get 0 over 0, which is not going to help us figure out the limit. So in this case, I know it's kind of strange. We don't usually rationalize the numerator. It's usually the denominator, but this is a case where it could help you. So notice I multiplied by the conjugate of your numerator. Okay, so if we multiply that all out, you'll end up with x plus 1 minus 1 over, notice how I left the x out, times root x plus 1 plus 1. So 1 minus 1 gives us 0. The x's cross out. You're left with 1 in the numerator and just root x plus 1 and then plus 1. So now we can put 0 in here. We'll have 1 divided by root 1 plus 1, which is 2. So our limit is 1/2. So again, next year in calculus, no matter which calculus you are taking, you will get way more into this. This is just scratching the surface. And here's the last thing I'd like to look at with you, is just if you are given a graph. And this is my key because I don't have a printer at home if you haven't caught on to that yet. Okay. All right, so use the graph above to evaluate each limit. Just lovely. Come on, this, okay. Or if appropriate, indicate that the limit does not exist. All right, so first one, the limit as x approaches -6, and then remember we talked about this back in unit 2, we have the little negative there. That means from the left. And for the sake of 2, 3, 4, 5, 6, of me not counting every time. So there's -6, and we want to know what is it coming in from the left. So I look, I'm coming in from the left of -6, and hopefully you're going to tell me that's -1, which it is. Okay, next problem. The limit, oh God, as x approaches -6 from the right. So here I am coming in from the right, and if I look at what's going on, what y value is it approaching? If I can count correctly, you should tell me 4. Next one, the limit as x approaches -6. So notice 1 and 2 were about -6, but they were from the left and the right. Now they're just asking, well, what is the limit of as x approaches -6 of this f of x? This graph here is your f of x function, if you didn't catch on. And so because -1 and 4 are not the same, it does not exist, D and E, because they do not match. Moving on to another one, number 4. The limit as x approaches -3 from the right. So -3 from the right. Well, we're coming in this way, and it looks like we are at -3. Now they want x approaches just -3. So just to be sure, I got to check both sides. So we never actually did a -3 from the left. Number 5 is just asking -3. So -3 from the right is at -3. -3 from the left is also at -3. So even though that's an open hole there, a circle, my limit is still -3. Okay, this is working really well. All right, probably just saw those answers, that's fine. So the limit as x approaches -1 from the left. All right, so we're coming in from the left, and so if we look, you should tell me that the limit's going to be 2. Next one, the limit as x approaches -1 from the right. So I'm coming in from the right, it's going to be the same thing, 2. Okay. Couple more to do here, and then we're done. Did you know you were going to get a concert today too while you were listening to your math video? I sure didn't. All right, so after 6 and 7, remember they both asked from -1 from the right and left. They were the same value. So therefore the limit of -1, because they were the same value, is 2, coming in from the right and the left matched. So now, random one, limit as x approaches 1. So notice we didn't ask you from the right or left, but you have to check and make sure it's coming in to the same number. So here's 1. Coming in from the left, it's coming to -1. Coming in from the right, it's -1. Limit of f of x as x approaches 3 from the left. Sorry. Okay, so 3 from the left, it's going down to -infinity. That's what it's coming in at. Limit as x approaches 3 from the right, that one's going to +infinity. So the limit of f of x as x approaches 3, again, this is your vertical asymptote situation. You got a -infinity, +infinity. This is your does not exist example. 13, the limit as x approaches 8 from the right. 3, 4, 5, 6, 7, 8. Okay, so 8 from the right, that's -infinity. Did I say -8 from the right? Sorry, 8 from the right is -infinity. And so this one, we've had a conversation in past years about what at this point we would accept as answers, but the limit of f of x as x approaches 8. So you might say, all right, well, the right we already established is -infinity, and the left is -infinity. So at this level right now, for just the introduction, you can either say -infinity or does not exist, because again, you have a vertical asymptote, and it's not actually approaching a value, it's approaching the negative infinity. So that was it. And way back when, one of you asked for a video. Did you want to sing my class a song? There was one girl in my class wanted us to sing one song from school. Okay, which one? Baba Black Sheep's not from school. Like Days of the Week. All right, well, come here. We'll put it on us and just. Okay. Oh, I look beautiful. Days of the week. Days of the week. Days of the week. Days of the week.
There's Sunday and there's Monday.
There's Tuesday and there's Wednesday. There's Thursday and there's Friday. And then there's Saturday. Days of the week. 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 Okay, well, thanks for watching all my crazy videos. We'll miss you guys.